You want to model everything in the universe and predict observables that can come out from experiment. We believe in Schrödinger equation and want to apply it to everything. No, you don't?
What? No, sorry.
I thought we believe in Schrödinger equation and Alice was showing.
You're in the wrong class.
But we did realize that if you apply it to molecules, there will be too many independent degrees of freedom. That is not possible for today's computers. So what we did, we formulated Hamiltonian, which you may look over once again in this little pathetic homework that I distributed. Do not spend more than 20 minutes. Just right. If it is 20 minutes, I'm tired. Then we formulated, based on this Hamiltonian molecular Schrödinger equation, and realized that we need to split it on several parts. So what are the parts? Electrons and nuclei, and later we will do further simplification. When we plug in summation of terms which are products of electronic and nuclear wave parts into the big molecular Schrödinger equation, we got something where electronic orbitals can be excluded from everywhere, and then it converts, if you drop non-adiabatic terms, converts into Schrödinger equation for what? For nuclear wave function. Right? And then I was noticing that when there were many equations, no one was taking notes. When I was writing one equation per slide, Alice was taking a note. So, definition of non-adiabatic cup. I will adjust teaching style probably. Only one equation per slide, and then maybe it is it finds path to your brains and hearts. Here is not my achievement; it's achievement of London, who told that nuclear wave function converts into delta function, and then we come into the idea of point charges, right? And then we decided that one day we need to speak about time dependence of the nuclear wave function. And here we come for the plan for today. This is time-dependent Schrödinger equation for nuclear wave function. We know that we are going to reduce it to delta function, or we are going to track only the center of this distribution, and we want to believe in another approximation that all nuclear wave functions are centralized around the actual position of nuclei. So there are not too many entangled superposition and Schrödinger cats in molecular world. You know, Schrödinger cat is when a thing can stay in two different places at the same time. The best thing about this part of quantum theory I've found on the website of anecdotes. If you are in a context of this Schrödinger and quantum function, at the time when you dress right sock, another one immediately becomes the left one. So it is a summary of quantum entanglement principle. We are going to go from this equation to Newton equation of motion for positions of ions, but we are going to do it carefully. If you believe in Newton's equation of motion for ions, then you can just lean back and relax. I will not tell anything new in addition to this. If you believe that once upon a time you need to write a comparative research paper and put some equations in support of this idea, you may follow and make some records, or you may not. This is not the most important meeting. So it is just for continuity of the material presentation. And we also rely on the concept of potential energy surface, which is energy of the system as function of elongations and contractions of interatomic distances that comes from nuclear repulsion and polarization electrostatic of electronic clouds adjusting to positions of ions. Some people, I just looked into Wikipedia, all this simple equation, electrostatic theorem, I felt that it is based on Feynman theorem, but they're simple guys. We just know from intuitive understanding. Positive ions, negative electrons, the resulting force is like adding them together will be something small. Good. I failed to do my main task for this slide. I need to draw lines here and support who like telling yes, yes or no. I think you don't mind, and you were not planning to do the slides this night. So I would do the slides last night before the presentation. So probably I have a little time to finalize list of speakers and the order. Yes.
So is it most likely we're going to be like doing 2 of these subjects due to we don't have as many people as subjects there are?
If you remember how we were doing in physical chemistry, I will do tricks. I will rearrange it so that it goes continuously. So, like, if London votes for these 2 things, I will call it number 7, and the rest is 888.
Okay.
Okay. So everyone will have one subject, but it will be a longer subject.
Okay.
And I will try to make sure that it is approximately fair, approximately even distribution, because otherwise it will be one topic will be longer and another shorter. It's hard to organize and follow. Please, Angel, please help to move this stuff to opposite corner. So, a great intrigue. Right now you will see continuation of this equation, and if you recognize what is after equation sign, you will not learn anything new today. So please, you can give it openly, or you can give me a secret sign. So if you are a little bit confused with these equations. Okay, thank you. So, why everyone respects or loves Newton? Because it helps to predict the future under approximation that everything consists of deterministic particles or solid like spheres or solid bricks. If there are no quantum, there are no electromagnetic, then Newton's theory is sufficient to predict everything in the future. Right now, we are coming to the aspect of life or aspect of chemical life where Newton will be very helpful. So if after some approximations we start to believe again that each nuclei is a point particle, and we want to predict where this particle will be after time interval delta t, then we need to know what is the initial momentum, what is the initial position, and which force will act on this particle at each next subsequent point of time, right? This doesn't surprise you. Okay. And then you can take acceleration, right? Integrate it twice and see how the position in space will be incremented. So it's standard type of Newton's equation. There is another one which may not always relate to the name of Newton, but it is the same idea. Instead of following only the position and having second derivative in the equation, one can follow simultaneously the position and momentum, which is harder. But on the other side, one will follow only first derivative, which is easier. So it's balanced. And it is same idea. If you want to predict where this single ion system of point ions, point charge ions will move, we saw this angular brackets tell to everyone who looks at our equations that we are so educated, that we know that in fact nuclei are quantized wave functions with distributions, but we are just taking expectation values. But in practice, it is just classical variable that we are tracking down. So so P is not position. R is position. Once I ran out of gas and was trying to find it on the highway and stopped at the stand-alone fireworks shop. Well, they shared half a canister with me, but the gentleman who was operating, like out of in the age, he told, well, he wanted to make a joke. When you look on your panel, E doesn't mean enough. E means empty. So P doesn't mean position. So when you want to see how the position is changing in time, it depends on velocity, right? Momentum divided by mass. If you want to see how velocity, momentum changes in time, it depends on the force. So force is the reason to change the momentum, or force is the reason to change the velocity. If you don't object and agree with it, then you are certified experts in classical mechanics. You can go to physics department and get full credit. And we are going to come to these equations based from time-dependent Schrödinger equation for nuclear wave functions, and just carefully go through all paths. In fact, we can inherit it from previous courses, but we better recall it. So it will be pleasant for me and relaxing for you. Do not put your brains under the turbo regime. Easy stuff. We got it. It was last time. Oh, okay. What did we do when we were on the lab last night?
You used Avogadro and
Yes.
that molecule, benzene?
Yes. Because you are so smart and educated, you were able to draw benzene. I tired after clicking on carbon 4 times. But we are just at the beginning, and we know that if you are educated organic chemist and you are sober, you will draw molecule more or less exactly. If you are not organic chemist and some other factors, I was drawing something like this. I was sober, but I was drawing it in the middle of the night. No one will accept it. So when you do it in Avogadro, you do optimize, right? Or rectify the structure. How do you do it? Maybe I need to stop and rerun. Right? So you observe it. So when you, right now we are just blind users, but in a moment we will become experts. So as you click this button, energy optimization, you see how bonds are contracting, and it's still going on. So it changes the angles and interatomic distances and dihedral angles to energy minimum, to such configuration which will not violate the eye of organic chemistry. Okay? And what does this mean? Which algorithm stays behind this procedure? Which equations are being solved? What's ridiculous?
Just a good wizard.
I don't remember what I was typing here. It was not this night. It was a couple of years ago. But we are assuming that for each configuration, for each interdynamic distance, by some reason, through the good wizard or through some algorithm, we do have total energy and we have gradient of total energy. We have force acting on each ion. And we can, at least for one infinitesimal time step, to go forward and see how the positions of ions want to change to follow this gradient. Right now, we are not discussing where this force is coming on, how this potential is calculated. Well, you know that it is based on solving Schrödinger equation for electronic degrees of freedom. And you need to solve it again and again at each interdynamic position. But there are some tricks in the community. I will not make an intrigue. It is called force field, when just forces are tabulated and reused again and again. But if you want to be precise, if you have heavy ions which were not tabulated, like uranium, you need to solve Schrödinger equation at each interdynamic position again and again. So there is, no, there is a single, but there are two aspects, two things. First, we kind of covered that we need to come up with Newton equation of motion that will help us to update positions if we do have forces. And second thing is where we take these forces, how to get this electronic structure, which I'm not going to address today. But these two things, in practical sense, are when you do optimized structure, ideally they need to loop together. You update structure, you update positions, you do electronic structure, you get new forces, you update positions, you get electronic structures, and repeat until the system becomes happy. If you are following this algorithm, we will return to it again and again, and it is one of the main ideas, iterative cycles. And this idea will be used again and again in many aspects, not only in geometry optimization. Okay, so I would like to quickly focus once again on the achievement by London from last meeting. So that wave function will be in the limit assumed as a delta function centered at the expectation value of position, or expectation value of position can be time dependent. I want to make a declaration, manifestation, disclosure, announcement. There are two types of computational jobs. One is geometry optimization and another molecular dynamics. In fact, they are different. They are being done for different purposes. But they are similar in several aspects. And one of the aspects is that one needs to know the potential energy surface and forces at each point. There is a way to combine them together. For example, if you do molecular dynamics with very large damping coefficient with the friction, if you provide artificial friction, wherever atoms are moving, they will stop and do not keep inertia. Then molecular dynamics under strong friction will be to some sense equivalent to geometry optimization. Okay? So if there is a force, it will go to the minimum. But as soon as there is no force, it will not continue to move according to inertia. While without friction, it will go like crazy to the minimum, away from the minimum, and again and again. So under strong friction, geometry optimization and molecular dynamics are very, very similar. It is more philosophical question to find their difference. London should believe in his own achievement. If some of you here in the class do not believe in it, we can go and try to prove, or at least to convince audience that it is possible. For example, if the potential energy surface is harmonic, which is not too far from truth if the elongation is small, then the nuclear wave functions look like eigenstates of harmonic oscillator, right? And then the width of harmonic oscillator does include the parameters mass, frequency, and Planck constant. And if the combination of this mass and frequency and Planck for specific, if they are much bigger, or Planck constant is much smaller than them, then the width of the wave packet for Gaussian wave function for ground state of harmonic oscillator will become negligible, or at least smaller than the precision of any measurements that we can do. For heavy atoms. For light atoms like hydrogen and proton, it is not always the case. But for most of the elements, it is very legitimate approximation. There's a continuous transition from harmonic oscillator Gaussian ground state to the delta function. No one objects. Good. In both quantum approach and classical approach, everything depends on Hamiltonian. If you are talking only about nuclear degrees of freedom, we need to have an operator that serves as a Hamiltonian for these degrees of freedom. And here we, Hamiltonian always include kinetic and potential energy. For kinetic, we already closed this question. If you neglect non-adiabatic couplings, it is just normal kinetic energy. And for potential energy, it is a summation of internuclear repulsion and electron cloud polarization, which depends on electronic state. And these things together do form potential energy surface. So now, how do we transfer from the quantum to classical case? Last time you did remind me the family name of the theorem. Can you do it once again?
Ehrenfest theorem?
Yes. Right? So what is it and what is that? No? Since you volunteered to name it, can you briefly cover what is it?
Yeah, so like it basically gives like relations for expectation values similar to the classical analog. So for example, like you can take the time derivative of the expectation value of position and recover like the expectation value of momentum from it.
Mm-hmm, mm-hmm. Please give me a little sign if this was not enough and additional clarifications are needed. You can give a little secrets. No one gives me a secret sign. You're fine with Ehrenfest theory. I don't believe you. I'm not fine with it myself. Maybe you just do not need it because of my announcement that everything what we do today is not needed for practical purposes. So and I know, in order to attract attention, I need to provide one equation per slide. Here there are about 6, so forget about it. So, if you were taking physical chemistry recently, this shouldn't be surprised to you. But if you may have heard this before, but the question is as follows. So we do have equation for distributed continuous function, wave function of nuclei, and we need equation for expectation value of some operator. For our practical reason, it is position and moment. How do we get this equation of motion for expectation value? If you scroll back to fundamental principles of quantum theory, you typically solve in a blind way. You solve Schrödinger equation, you find wave function as at any position and time point, and then you do integration along the position to find expectation value, which is correct, but not always efficient. If we need expectation value, wave function includes all possible observables. But if you need just couple, why don't we reformulate equations only for these observables? Right? So one can convert time-dependent Schrödinger equation into equations for such observables. Right? You recall it. So if you have this wave function, you have definition of observable and we apply time derivative, and then we open it by differentiation of product. You see that includes differentiation of left wave function, right wave function, and operator itself that we can drop. But the differentiation of the either left or right wave function is nothing but acting on Hamiltonian operator on this wave function. Right? And when you plug it in, you see that your operator, this stuff, is replaced by this stuff. This stuff is replaced by this one. And it looks almost the same, with the only difference that operator, which for us will be positional moment, and Hamiltonian are in a different order. So, which is equation of motion by Heisenberg for any operator. And if we plug here position and here our Hamiltonian for nuclei, we will see how the position and momentum will evolve in time. So we do not, although we are observing these equations, we are not deriving them in this course. They were derived and discussed 50 years ago, 50 years before first computer program for electronic structure was set up. It is very basic information. But now it gives us a way how to go from wave functions to point charges, to propagation of point charges in time.
I have a quick question.
Yes, please.
My last slide. What differentiates the difference between the left and the right? How are they different in any way?
I was expecting the question. And
because my problem with it is why doesn't that just equal 0 consistently?
what is not equal to 0?
HA minus AH. Do you get my question?
Yes, I got your question very well.
Okay.
And I have an idea how to answer it. I'm just finding the best way and quickest. So first, I need to refer back to PChem course where you were representing each operator as a matrix. And if you just make a numerical experiment of multiplying two matrices in one order and another one and subtract, it will be not equal to 0 for many matrices.
Okay. Yeah,
Okay?
I do remember that.
Yes. It means that operators or matrices do not commute. Sufficient?
Yep.
And left and right, this is abbreviation for wave function and wave function conjugate, with and without star, as a row and column, if you speak on the language of linear algebra, row and column vector. And by row and column procedure, if you have wave function saved as a row, then you need matrix acting on a row to practice row by column rule. If your wave function is column, then you need column by the matrix, different order to practice row by column rule. In some sense, we can say that here Hamiltonian acts from left to the right, here from right to the left. But it's only symbolic.
Okay, thank you.
So, do not stop relaxing. It's only illustration. What is the simplest Hamiltonian?
Free space.
Yes, which is kinetic energy. And if I'm so lazy that I set up mass equal 1, well, all constants are 1. So, and for example, I want to focus on the Angela, may I ask for help? Move this panel down to this point. So, if I do want to follow the time evolution of the position of r, dt, this is not v, this is my t, pardon my calligraphy. And it should be constants, I, h bar. Is it in numerator or denominator?
H bar is in the denominator.
Okay. Plus or minus?
Minus.
Okay. I don't know. So we need to put Hamiltonian and position, both operators. But if we set up Hamiltonian p squared over 2m, but we can forget about 2m, just p squared. M can be tracked down later. Then we need to check that the operators of p, second power, and r, first power, we just need to open this bracket. So this rectangular bracket is this stuff minus this. So this was p squared, p, p, r, minus r, p, p. I do not have a speech defect. I'm just opening the expression. And then referring back to very, very relevant question by Austin. Like, how do you know that certain two things are not zero? In addition to equation for momentum in quantum theory, there is another equation that one may want to memorize from background quantum. Commutation of position and momentum. If you swap order of position and momentum, based on the differential properties, it will be operator imaginary unit times h bar times identity matrix, if it is in metric, right? Or based on this commutation, one can replace rp as I h bar plus pr. So we are going to plug this into here and then practice it once again and recast this line in such way that we will have momentum and position in the same order in each term, wherever it is possible. So through application of basic commutation rule, here, once and second time, we will see that it will be PPR from here, another PPR from there, but as a price for swapping order of operators, you have this minus 2i h bar p. And this commutation operation converts, it gives us momentum operator. So originally we started to look at the time evolution of position, and at the end we got the expectation value of momentum. And if you want to be rigorous and meticulous, we will put divide by 2m somewhere, which is very hard to fit into the screen with my not precise hand. Okay, so you see the first of these equations of motion that we need. Time evolution of position depends on momentum, and it goes along with your intuitive understanding. You do not need to be in computational chemistry class or in physical chemistry or even in physics. You know that if an object has non-zero momentum, if it moves, intuitively it means its position is changing. Nothing else. When you do the same thing for the momentum, one will find that the result through these commutations will include gradient of the potential in respect to position, which is force. It is another thing that one can, well, I do not request you to memorize anything. I do not count on my own memory and do not want you to count on your own, but if you were ever taken or plan to take introductory physics, it's also one of the things that one can memorize from there. That derivative of energy, potential energy, gives force with minus sign. And some people, if they want to look smart, they call it gradient. So gradient of potential energy minus gradient of potential energy is force. And here we are coming that change in time of expectation value of momentum is this thing. I didn't complete the equation here, but it should be a little later. Good. You see the word force? If you see it, you can skip whatever is above. Convincing, right? So and it comes from carefully plugging in this commutation thing. If you are really meticulous, you may ask why there is a commutation only between P and potential energy, whereas why kinetic energy is skipped. Because kinetic energy consists only of momentum, and momentum with momentum commutes. Like things of the same nature commute, they change of order is zero. So, if we are still in the language of quantum theory, instead of this angular brackets, we can put this Dirac notation and wave functions. Okay. But so that if it is quantum case, then the idea is that force that influence change of momentum comes from expectation value of the gradient of Hamiltonian or gradient of potential energy surface. Expectation value of gradient of gives force to change momentum. Okay, I will circle around this idea by either words or equations, but we are not going to go too much further away from here. So, and now we have set of two closed equations. So position depends on momentum, and derivative position depends on momentum. Derivative of momentum depends on derivative of the potential energy over position. So if one does have this U function, this set of equations, closed equations, connected equations, can be propagated simultaneously. And as a result, we will know the position and momentum at each point of time. If we add friction, this evolution will bring us to the minimum. What do you mean I cannot ask you, what do I mean propagating time? So if we numerically solve this equation, it means we are going forward from value of this expectation values at time t to the value at time t plus delta t. Just make one step forward and then another step forward. So stepwise propagation in time. Okay. Earn fast. So how we can summarize what we do and where we are, and what do we expect to see if you will be persistent to join these meetings next week. So we did. By the way, we soon are finishing the first theoretical chapter out of 4. There are a total of 4 chapters. So first is this senseless background information. Second will be a way to solve electronic structure theory for many electronic wave function by finding a way to project it on many one-electron functions. In essence, in general description, and with the precise terms, it will be Hartree-Fock theory. So whatever, about 7-8 meetings for this background, then about same amount of meetings for Hartree-Fock, then another chapter for density functional theory, and then another one for excited states theories, and then we'll be done for the semester. So we are coming close to the end of the chapter, and we agreed that there are molecular Hamiltonians, there are molecular Schrödinger equations, and one do want to split electronic and nuclear degrees of freedom and write specific equations for each of them. So for electronic degrees of freedom, you put electronic kinetic energy, electronic repulsion, and electron nuclear interaction as electronic Hamiltonian. And we will solve this equation in the next chapter. This stuff is needed. This eigenenergy that parametrically depends on positions of ions is needed for nuclear part. In the nuclear part, we do have Schrödinger equation for nuclear wave function, or we can formulate it in the form of time dependent. And then we are making transition to a classical limit. In more rigorous courses, not computational chemistry, but quantum 2 or whatever, one tries to justify when this transition is allowed or not allowed. Here, we need to accept it because nothing else is possible. Just by the level of today's development of computational facilities, one cannot solve together electronic and nuclear wave function at the same time for all degrees of freedom. Some brave individuals do research on nuclear wave function, but you may have noticed that it is done for maybe 1 or 2 degrees of freedom, not for all 100 of those. For all 100 of those, it's too early for today and for next 10 or 20 years. So therefore, possible or impossible, but one goes from wave function to expectation value of position. And then by expectation value of the gradient of this electronic part and the gradient of nuclear repulsion, one is getting force that is plugged into a Newtonian equation of motion. or this coupled set of equations of motion for position and momentum. When these equations would include additional term for friction, they would be equivalent to finding minimum, to optimization. Although strict optimization is a little bit different. There is a so-called steepest descent algorithm according to gradient, and we will cover it as well. But this is the quickest thing to wrap up our mind around how we are optimized geometry. So our goal that we should be ready to accept and understand in very soon is how to practically optimize any geometry and what does it mean to optimize geometry, which things are behind it. Then, after we will get optimized geometry for our models in the practical side of the course, we will focus more on single point calculation. If all positions of all ions are nailed down and do not move, how to find electronic structure, how this electronic orbitals or overall multi-electron wave functions distributed in space and which energies eigenenergy does it provide. Do we want to see anything else? No? Yeah, it should be end of the. Yeah. I will stay here to answer any questions, but the meeting is done. I volunteer to finish the list and distribute it to you as soon as possible, but my latest deadline is Sunday night. I'll try to do it early so that you have more time. Meeting is dismissed. Have a nice Friday and following weekend. And I'll stay here to answer any questions if needed.
Yeah.
Statement.